Let's continue with the L2 projection. The L2 projection is a mathematical tool, but can also be interesting if you want to substitute an arbitrary function f, which is in a space L2, by a piecewise linear approximation, because if you want to do some integral calculate, you want to do some integration or other things which would be easier with a piecewise linear function, that could be interesting. But here in the lecture would illustrate the assembling of the mesh matrix and later on the assembling of the stiffness matrix. Therefore, I just focus here on the L2 projection. So for the L2 projection, we need the space of square integral functions, which is denoted by L2. We consider real valued function, and the property is that the integral over omega, the absolute value of u squared, is less than infinity. It's quite often written with these absolute values because you can think about complex valued functions or vector valued functions, then you have the same notation. The L2 projection itself is defined as a projection of a function f of L2 onto the space SH, and the function, this pH of S is an SH, has to satisfy this f minus pH of f multiplies VH integral over omega dx is equal to 0. That means the error, this is the error you will make, is orthogonal in the L2 product, is orthogonal to the test space. Always think about it's just a projection onto this in such a way that the error is orthogonal to the test space. Okay. And this space SH is, we defined before, as a finite dimensional space and spanned by the basis functions phi I, our head functions. So this is equivalent to this expression. Of course, if you have this, all these functions in VH and SH can be represented by a linear combination of phi I, and on the other way around, even the head function or the basis functions, head functions, are one element. So this also is satisfied for all functions and of course for the head functions. So this has the equivalence. And since we map into this space as H and the phi H are a basis, then the pH of f can be written as xi j times phi j. Of course. And n index c is the index, it's the number of our nodes, or the dimension of our coordinate array, which is n index c times 2 in 2 dimension. Okay, now these problem written here, we run this way that the PAF of P of f times Vi can be computed and it's known, so we write it on the right hand side. On the left with the unknown we have our projection, and projection times our test function. The integral is linear, so we take the sum and the coefficients out of the integral, that these is independent of our coefficients. So we have to satisfy sum times coefficient times unknown times some given coefficient equals right hand side. We use the notations for the mass matrix. It's related mass matrix because this matrix originally arises in some elasticity problem. We have some stiffness of some elastic material. You have some mass properties which give some different behavior, some damping, and therefore these the expressions mass matrix, stiffness matrix, and load vector come originally from. So we have this mass matrix for this part, and these just mij with the integral over omega, head function index j, head function index I, given, and the load vector is just this coefficient here for all. We have to satisfy this for all I from 1 up to n index c. So this expression here, when we substitute the integral by mij, is this term. It's the same. And of course, you know that is just simple writing of, or it can be simplified in this matrix equation. The matrix M itself, as you see from the coefficients, is symmetric. So the integral, or you can interchange phi j and phi I, makes no difference. And the question is that the matrix is positive definite. Therefore, we can have a look at the following proof. We have to prove for an arbitrary, or we choose an arbitrary vector xi, multiply with from the left to the right, using the definition of our matrix elements. The matrix elements are just the integral phi j, phi I. Then we have two sums. We have one sum now with the, if we take the integral out and the sums inside, two separate summations. And the summation gives now the, it's nothing else that we have the L2 product of two functions. So this phi I is a function in x and y, and this function should be 0. But due to the case that our functions phi j are linear independent, by construction we know that this has to be larger than 0. Okay, make under the assumption that our vector itself, it's not the trivial 0 vector. Okay, we have, that's the computation of the mass matrix. For the load vectors, in general, we have an arbitrary function f. Of course, we assume that it's some way that we can have some point evaluations, and we can apply some quadrature formula in such a way that we can compute expression of this term. So this f here is generalization of, for, we have to compute this here. So f phi I now is given here. This is for the whole term. There we weights and the function we have to integrate, would like to integrate. So there are mainly three simple rules. So that's the center of gravity rule, where we, at the center of gravity, we evaluate the function f. If the function f would be constant, this gives an idea for the quadrature weight. Of course, then it's just the size of the, or the area of the triangle would be the quadrature weight. If we have some corner quadrature formula, of course, then it's obvious that the quadrature weights are area of the triangle divided by 3. And similarly, when we evaluate the function at the midpoints of each edge, then again the quadrature weights are the area of the triangle divided by 3. Okay. More precise, the function, the quadrature formulas have this form. You see again the weight over 3 and the evaluation at the midpoint of an edge. Now, we consider a simple example. We have a domain. We have given here triangle T1 with node N1. Oh, that should be N4. And this should be N5, N2, and N3. And we would like to compute this mass matrix. So instead of taking the integral over the whole domain omega, we split into three integrals over the three separate triangles, and each integral of a triangle gives us a 5 by 5 matrix. So once again, let's have a look. For the first triangle, we have the nodes 1, 4, and 5, and phi 2 is 1 here, it's 0 there, 0 there, and also 0 there. So phi 2, which belongs to this node, is 0 here, there, and there, so it's 0 on the whole domain. The same with phi 3, which is 1 here, 0 here, there, there, and there. Of course, it's 0 on the whole domain T1. Okay, this gives us the rows here and there. For the second triangle, then we have only, this should be 5 and this should be 3. So phi 3 is 0 on the whole T2, and the same for phi 5. 0, so we expect zeros for the third and for the fifth row. And the same now if this is 2, 3, and this is N4. For the first and for the fifth node, we expect 0 rows and column, which is given here. All the time when we're doing these calculations, these matrices are 0 up to at most 9 entries. Okay, and this idea we will use for computing the mass matrix and computing the stiffness matrix. And of course, if you at the end of the day, you have to take all the integrals over all these separate triangles, and you have to add one matrix to the next matrix to the next matrix. You shouldn't add all these zeros to the matrix. So if you do the summation of your n times n matrix, why you should add zeros on top of zeros on top of zeros? You all know that it's only a few times that you add some entry at them. Now we have to compute the entries in our mass matrix itself. Therefore, we will use the analytic formula where we have our 3 head functions belonging to our triangle to integer powers r, s, and t. And by induction, you can derive the following solution, which is just 2 times r factorial, s factorial, t factorial, divided by the factorial of r plus s plus t plus 2 times the area of t. So if you generalize this formula to a simplex in arbitrary n dimension, then you will see that this 2 will behave like the dimension, and also this 2 here will behave like the dimension. Okay, and if we do the computations for all 9 combinations, so phi 1 times phi 1, phi 2, phi 1, and so on, you will end up with this local, because it just belongs to one element, this local mass matrix. And this mass matrix can be rewritten as 1 over 12 times the area times 1 plus the Kronecker delta ij, which is just 0 if it's not equals j, and 1 if it's I equals j. So how to compute the right hand side? There we use the node quadrature, and the node quadrature we have to compute this by the node quadrature, so evaluating as 3 nodes around. But now if we have phi I is 1 at the node I and 0 at all the others. So this gives phi evaluated as ni times phi I at ni, which is 1, plus phi of n, another n, but not phi I, not ni, and there is the phi at all the other, at the both other nodes is 0. So this simplifies to this expression where we use the node quadrature. Okay, so if you plug everything together, we have the following subroutine to compute the L2 projection, which is we plug in the coordinates, the elements for our geometry, and the given function f. So as you see later, and it's obvious that the matrix M is sparse, so we initiate this sparse matrix with the dimension we expect, size coordinates comma 1, a square matrix, and now we have a loop over all elements. So we take the first 3 global coordinates. So we know, okay, when we compute now these 3 by 3 local matrix, we should know where to place it in the global matrix. And I mentioned before, we don't want to add all the zeros when we take the integral over T1 and then all test functions. We know that a lot of integrals are 0. So therefore, we have this nodes variable taking from coordinates nodes, which is a 3.1 or 3 vector of length 3, comma double dots. This gives us just the 3 or the x and y component of the 3 vertices. And this is the matrix 1, 1, 1, x, x1, x2, x3, y1, y2, y3. And the determinant then is twice the area divided by 2 gives the area of our triangle. And this is the formula we've seen before, and now we assemble by a for loop over all elements our mass matrix. And of course, even that we have a loop over all, if we have in mind, we'll loop over all basis functions I over all basis functions j over all triangles, so which will be 3 for loops. But we see it's almost linear because the for loop we have is just a 3 by 3 and it's simplified to adding these mass matrix. Okay, and I guess this is everything. The L2 projection. The L2 projection is given here and some program to run the example simplified here, but I guess we do a small Matlab session right now. Let's do an example. So we have here the L2 projection, the example given in the slides, and if we run this example, we have for this very coarse triangulation, we will end up with this result. So very coarse, of course, and we would expect that the solution is similar to x times y. There's some kind of symmetry, but here we're far away from the exact value, and here we are far away. Therefore, we run this example with a finer mesh. Before we start writing a mesh refinement procedure, we'll use the mesh generator as shown in the examples 1 up to 3 and also in the slides. Therefore, we'll copy the commands, so the geometry and the elements and coordinates. Therefore, we create a new file for the generation, and therefore we copy this, copy here, and put this on top, and delete these parts, and delete everything that's given here. So we need at the end some matrix. We've given 2, and then the start point will be 0, 0, and 1 is on the left and 0 is outside. And we also need the end point will be 1 and 0. So first segment of describing our geometry will be, we have a line starting at 0, 0, and we end up at 1, 0, and 1 is the domain on the left and 0 is the domain outside. So the next segment will be 2 starting at 1, 0. Run this, so save this as a new example and run this example. So some mistake, oops. Extra character. Oh, let's do it like this way. Okay. Here we see more or less the result we would expect, closer to the result we would expect. Take a finer mesh. And now the result looks more closer to the function we would like to expect. So let's say it's 0 along this side and this boundary part, and here we have from 0 up to 1. Okay, the question is, it's not even that we have a piecewise linear function. Why does not show the exact, or not a better approximation? We have, the first reason is that we start with a linear function. So in each triangle it's a plus bx times cy, but the given function is x times y, so we cannot represent it with our ansatz space. The other point is, let's just take the function x and do the calculations. What would we expect? Here we would expect that we exist in our ansatz space, but the result, why do we have these wrinkles at the beginning, at the end? So is this by solving the linear system of equations? So the mass matrix we compute is exact. We solve the linear system of equations, but if we have here size the size is wrong, it's size elements, size coordinates, gives the, we have just 185 unknowns, and these wrinkles here, or these oscillations, are too much for just rounding errors for solving the linear system of equation. What could be reason for these errors? Not the mass matrix, not solving the linear system.